Hello everyone and welcome to my channel. In this episode, I would like to share something about this industrial standard RF generator board with you. This board is used to generate high energy density, high temperature plasma. Without going any further, we should first know what this board is used for. This board is taken down from a Perkin Elmer laboratory equipment which is called a gas chromatograph, and the equipment's function is to analyze the test component and can tell the content of different elements. The equipment employs spectrum analysis to achieve that function. However, that means the test component which will be tested needs to be heated into free atoms. There are a few ways to get the needed high temperature, such as a graphite stove, flame-heated system, and also a plasma system. So this board here is just the RF generator board itself without the two main resonant capacitors and the main resonant coil, and also the two feedback capacitors. This is a push-pull type Class C oscillator. Here is the schematic itself. This one here is this board. Here I borrow the word push-pull because the exciting current in the resonant tank circuit, which is here, is generated by grounding one side of the tank circuit, which you can see these two nodes, to the one side of the resonant tank circuit is brought to ground, while the other node is connected to the plus supply through a current source, which is this inductor, right? So this is something like a push-pull type resonant circuit, but without a central conductor. This circuit looks quite like a ZVS circuit, right? In a ZVS, generally we will have two feedback diodes here, Schottky diodes here, and in this RF circuit we use two 33 picofarad RF high voltage capacitors to realize that feedback signal. So let's take a detailed look at this board. First, I need to say that since I do not have the two feedback capacitors in today's video, we will not do any test or anything else. We just take a look at this board. Also, the main resonant coil needs to be made out of some copper pipes, but that is not hard. And in next month, I will be able to get the two feedback capacitors which will be mounted here. Let's take a look at this board first. You see, here is the power and the control connector, right? So here and here are just some filter capacitors, and this one here is the temperature sensor, just a thermocoupler. Or maybe not a thermocoupler, it's just a thermistor resistor. And here are two main RF MOSFETs, which is generally MRF 157. They can handle 125 volts, while 40 or 50 amps, I can't remember clearly, but maybe something around that. And also these are two RF chokes. You see in the schematic here, each of them is 360 nanohenry, made by micro metals. The core is made from the company Micro Metals, because it's RF type core. And these are two relays The function of the relay, we will talk about that later. And this is a drain, this is the drain, this is the gate, this is a gate. Very simple, right? Just exactly the same circuit as a ZVS circuit. So let's follow the current path. First, the plus supply here flows through this current sensing resistor, which is 0.02 ohms each. And through these filter capacitors, through this trace to this choke to the drain. Also here is the same. And after that, we will have two capacitors, this one and that one. This is a RF high voltage, high current rating capacitor, a doorknob capacitor. Some amateurs like to call it in that name. And it's rated to this 160 picofarad, 13 kilovolts peak to peak. And these are two ports, which means the capacitors will be mounted here, right? These are silver plates for better conducting the RF current. Also, you need to notice that these two bolts are non-magnetic. They are made out from copper, because if you use any magnetic metals in a RF current loop, it will generate much heat. So it's very important to use these bolts, not just a handy bolt. You take it and mounted it here. That is not right. Okay, and here are 4 ATC RF porcelain capacitors, and there is another one here, which you can have a clear look on this side, right? So what is the function of this capacitor here? We look at the schematic here. We can see that this is a 1000 picofarad capacitor in series with a relay, and they connect this node, which is the drain of the MOSFET, to ground. And that is for the starting process. During the starting process, these two relays will be closed, so the drain will have more capacitance to ground, which means a lower impedance here. That will generate a higher voltage across the tank inductor for an easier starting process of the inductively coupled plasma. We will talk about that later. So this relay, this capacitor, and also these two ones are used for starting process, and after that the relay will be opened, and this capacitor will be disconnected from the circuit. Also, if you take a closer look to the relays, you can see maybe it's not that easy to see, but okay, I turn on the flashlight here. You can see the relay has a glued gasket here, which means it's a gas-tight enclosure box. That means the manufacturer may have some failures of the relay during the test because of the moisture in the air, right? Because it's a RF circuit, and they just use I think they are just some standard type relay. Maybe they have a larger distance between the connectors. But if that is in a RF amplifier, we need to use some vacuum relays to do this job. But they simply use the cheap, maybe not that cheap, but cheaper than a vacuum relay, right? So starting circuit, And let's take a closer look at the bias circuit here. You can see the bias, right? Here is a bias, and it's very simple bias circuit, just like in HFSSTC circuit. So that is not that complex. Also, the bias is controlled by the microprocessor in that equipment, ICPOES equipment. Also, the plus supply is regulated by the microprocessor as well. In the document PDF, the manufacturer says that they can vary the RF power from 500 watts to 2300 watts by accuracy to 1 watt. That is very accurate, because in such an equipment, gas chromatograph equipment, the RF power has a great influence on the result. Okay, and here is another type of the same circuit. I just draw half of the circuit. You see, this is the node at here, and this over here are just this part, half this part of the circuit, right? So what is this circuit here? If you are familiar with Marzilli ZVS circuit, you may know that there's another version which employs another MOSFET, smaller MOSFET, to drive the gate of the larger MOSFET. This is the same function. This circuit functions the same as what I said. It utilizes inductive feedback here, just some type of current transformer, and to drive this smaller MOSFET, which will control the bias to the larger MOSFET's gate, right? For better driven of the MOSFET. Sorry for my English. Also the feedback capacitors on this circuit, which are here, I just mentioned, are 33 picofarad and rated to 7.5 kilovolts DC. HT57 is its type, if I remember correctly. And also here and here are P-channel, N-channel MOSFETs, which are used to control the gate voltage in an emergency situation. And here are just some resistors. 4 resistors. Here and here are 2 Schottky diodes, which can function under 200 megahertz. And it's a simple board. Also here is a fuse, and there is another fuse under the board, but since maybe I won't disassemble the board from its copper. You see the copper heat spreader and the water jacket here. It's a water-cooled RF generator. Very heavy, maybe I think it's 5 kilograms. It weighs around 5 kilograms. And this board is very expensive, but I get it from a foreign friend which works in a chemical company, or maybe not a chemical company, environment analyze system in Thailand, and he gave me this board. So I only spent around 10,000 baht, maybe equal to maybe $300, I think. It's cheap, right? But without the main resonant coil and the 2 feedback capacitors. And I have found the 2 capacitors from the original company, and I have ordered them, and they are on the way to me. So after I received the capacitors, and I will do a more detailed video about this circuit. Also, you may wondering what is an inductive coupled plasma. So let's take a look. And I think on YouTube, Tate has some excellent videos about inductive coupled plasma. You can search for his videos on YouTube, and he also makes some quite nice global discharge in a glass ball. That is quite nice. So we take a look at this inductive coupled plasma. This in the first row, the first two pictures shows that plasma is excited by a spiral inductor, and in the second two pictures we can see the plasma is excited by some planar inductors. These are just two metal plates made to a ring shape, and it has a cut in the middle, so it's not a shorted ring, right? And one side of the ring is connected as this inductor, one side to the resonant tank, and another side of this upper plate is connected to the central metal block, and this side of the lower planar connects to the central conductor plate as well, and another side of this the lower planar connects to the another node of the resonant tank circuit. So it also forms two turns of inductor, like this one, two turns of inductor, right? These are inductive coupled plasma, and the company says that by utilizing a planar shape of the inductor, they can achieve a more uniformly distributed temperature field, maybe, and that is all about this board. And while I am searching for the information about this board, I also noticed that in a US patent, maybe some first semiconductor ICP system, they utilize the MOSFETs just like in HFSSTC, just some switching type MOSFETs, and they just use the exact same circuit as a HFSSTC, which is working here. The exact same circuit, but they utilize a series gate resistor, which is shown in my 3.6 kilowatt HFSSTC, maybe in January or February, in that video. If you like to check, you can go and see it. They use a gate resistor to adjust the power, and the patent says that it should be adjusted to the maximum power. That resistor should be adjusted to the maximum output power of the oscillator. And actually, I am wondering which type of resistor they were using, because that resistor needs to be very low parasitic inductance. It needs to have a very low parasitic inductance, and also high frequency current will flow through that resistor, so the resistor will generate larger amount of heat. I guess maybe they use a switch to adjust different resistor values, but not very fluently adjust. Maybe, I don't know. And I know that the resistor's value is around 1 to maybe 1 to 5 or 1 to 4 ohms. So that is not a very large resistance and not a very large range. Maybe I can try it, but I really need some heat resistant glass tube with some gas filled in. Now I just use a CFL, and in my previous videos you can notice that I use a neon gas tube, but unfortunately that quartz tube actually melts under around 120 watts RF exciting power. And I have also destroyed maybe 10 or 15 of these CFL tubes because of the high temperature, and sometimes the tube just melts and form a hole inside because it's a negative pressure to the ambient pressure, right? It just forms a hole in the tube and the tube is destroyed. But fortunately, these tubes are from the broken lamps, so I do not spend any money on them. It's very convenient, but I do not want to change the tubes. Also, I want to experiment with higher power rating. Maybe I should use a test tube filled with some non-conductive liquid inside the test tube, and put the gas-filled quartz tube inside the liquid to form some kind of liquid cooling, but I'm not sure which liquid will I use. I do not want to use oil because it will make a mess, and also water is maybe not certain. Maybe water is not functionable because it's conductive, but maybe under high frequency, I don't know. And also alcohol is very bad because it is flammable, and I do not know what kind of liquid to use. So if you have any thoughts, please comment under this video, and thanks for watching. If you have any questions, you can ask me for free. Just comment below or send it to my email, which is shown in my channel's title. And thanks for watching. Wish you to have a better day.